Hey Trig, this last section is going to be, well, it starts off anyway with some familiar territory. Okay, we're going to go back to algebra a bit. How would you solve this equation? Hopefully you would subtract 6 and divide by 2. You get x squared is -3. Typically we would stop there. Okay, in 9th grade, etc., in Algebra 1. And then in Algebra 2, we realized that René Descartes invented the imaginary number to help us work with real numbers and get back into the real number system. There's many places where imaginary number is used in order to work through problems, which eventually get you back to the real number plane. Okay, I take the square root of both sides. You're like square root of -3. If I do that on my calculator, I get no real number. However, hopefully you remember this, that the imaginary unit, the lowercase letter I, usually italicized, is what René Descartes invented. He let I be the square root of -1. So that we could continue to solve this problem. -3 is -1 times 3. So I can make this the square root of -1 times the square root of 3. And now I write the final answer as I square root of 3. Oopsies. Of course, I'm so excited about the I that I forgot my plus and minus. There are two answers, plus or minus I square root of 3. Okay? The imaginary unit I is the square root of -1, which means that I squared, when I square both sides, I get -1, which is real. All right, so there's ways to work with imaginary numbers, getting us back into the real number system. So there are problems that we before had to stop with that now we can continue with. That's why they're so useful. Okay, this is the true list of numbers. We give, in high school, we live here, right? With a little bit of this and maybe some algebra 2 or pre-calc, whatever, but we don't really work with it. However, as you get higher and higher up in mathematics, you realize that this is the complex number system. Okay? Half of them are real numbers. We cut this Venn diagram in half. Here are all the types of real numbers. Notice how we call a real number. A plus bi, where b is 0. A plus 0i means there isn't any, there are no, that term goes away and I just have this real number part. Non-real complex numbers are a plus bi when b is not 0. I have an imaginary part. 7 plus 2i, 5 minus I square root of 3, -1/2 plus 3/2 I. A pure imaginary number is when a is 0. You don't even have a real number added to the imaginary part. It's just 3i, -I, -2/3 I squared root of 5. We just have the bi part because a is 0. That is finally your senior year, right? End of TRIG, couple weeks left, and you've got the whole number system now. Okay? Of course, real numbers, we know, we've been studying these forever. Real numbers are either rational or irrational. In other words, you can either write it as a fraction or you can't. Okay? Out of the rational numbers, we have the integers, where the denominator is 1, basically, in the fraction. Okay? We have the whole numbers, which don't include negatives. And we have natural numbers, which is how we naturally count things. If I want to see how many kids are present, I go 1, 2, 3. Right? I don't go -3, 2, or whatever. Okay? Anyway, we know those. It's the fact that we never really knew. We stayed here. We never really knew. All the entire number system is called the complex numbers. A plus bi, where b is 0, those are our real numbers. A plus bi, where b is not 0, those are our non-real complex numbers. But real numbers are considered complex numbers. Okay, little twist there, huh? All right. What we want to do is make sure that we can simplify these. I know you've done these before. I always just figure it's like I take this -16 and make it -1 times 16. I take negative 70 and make it negative 1 times 70. Negative 48 is negative 1 times 48. That way, I figure the square root of negative 1 is I, so I have I squared to 16. I have I squared to 70. I have I squared to 48. We're not done, okay, but we at least took care of the fact that there was a negative under the square root. Now I simplify. What is the square root of 16? We've been doing that since Algebra 1. Square root of 16 is 4. If I really wanted to write it as a complex number, I might write 0 plus 4i, but you don't have to do that. I think that's silly. We don't need the 0 there. We understand that the real part is 0. 70. Ugh, I don't think I can do anything with that, right? It's 7 times 10. 10 is 5 times 2. Yeah. There are no perfect squares as part of 70. I'm going to keep that the way it is. 48, however, is what? 16 times 3? Okay. So I have the square root of 16 times 3, and I can take the square root of 16. It's 4. I'll bring that out with the I, and that final answer is 4i squared to 3. Notice we don't write 4 squared to 3i, only because sometimes people end up extending their square root, and it looks like is the I under the square root or not. And it's just not. It just doesn't look right. Okay? Pull the I in front of the square root, like they showed you here. If it's just a number times I, that's fine. But if it's an irrational number times I, write the I first. Solving these equations are just like I did on the other side. I'm going to take the square root of each side. So I get x equals plus or minus I square roots of 9. So x equals plus or minus 3i. Here, x squared equals negative 24. Square root of both sides. X equals plus or minus. I can think of this as negative 1 times 24. So that's plus or minus I, square roots of 24. However, 24, if I go off to the side, I know that's 4 times 6. And that's all the further I can really go as far as a perfect square that's a factor of 24. So I have plus or minus I times the square root of 4 times 6. Square root of 4 is 2. Plus or minus 2i square roots of 6 will be my final answer there. Here I have 9x squared minus 6x plus 5 equals 0. Boy, I'd love to factor that if I could, but I can't. I'm going to take the opposite of b, plus or minus b squared minus 4 times a times c, all over 2a. We get 6 plus or minus the square root of negative 144 all over 18. So that means I have 6 plus or minus. I know that the square root of 144 is 12. This is negative 144, so it's 12i. Okay, now I still have people having trouble simplifying these. Since these are connected by addition, I have to find something. If I'm going to reduce this, I have to find something that goes into 6, 12, and 18. And since 6 does go into 6, 12, and 18, I'm going to take 6 divided by 6. I'm going to take 12 divided by 6. I'm going to take 18 divided by 6. To write this in true complex number form, I would write 1/3 plus or minus 2/3 I, so that I would realize the real part is 1/3, the imaginary part is 2/3 I. Okay? Alrighty. Here we go with multiplying or dividing. All right. Notice we have the word caution down here. That's because you want to be careful that you don't multiply first, guys. It's the only time. We always say, like in other words, if I have square root of 3 times the square root of 6, that's the same as the square root of 18. I just multiply them together before I simplify, okay? Not the case here. When I have negative under the square root, you want to, this is going to sound funny, but take your I out first. Don't physically take your I out, okay, guys? Take I out first. I shouldn't have said your I. Take I out first, okay? Otherwise, this is going to be square root of 49 because a negative times a negative is positive, and you're going to be like, oh, this is just 7. No, it is not just 7. Okay, that's the wrong answer. Okay, so that's why we caution you on this, okay? Dealing with imaginary numbers is a little bit different. Just like every other sets of numbers, we have ways to add, subtract, multiply, and divide. When you're multiplying, adding, subtracting, whatever, you put it in complex number form first. So this is I squared is 7 times I squared is 7. So that's I squared times the square root of 49, or I squared times 7. What we saw on the other page when we first learned this, that I squared is negative 1. So anytime I have an I squared in a problem, I am going to write negative 1. This is negative 1 times 7. The answer is negative 7, not 7 like I would have gotten if I would have multiplied first. Take I out first. Okay? So I have I squared is 6 times I squared is 10. That gives me I squared times the square root of 60. Let's see, 60 is 6 times 10, obviously. 6 is 3 times 2. 10 is 2 times 5. So I really have what's 2 times 2? 4 times 15. I'm looking for perfect squares. Square root of 4 is 2. So I have 2I squared. Oh, I'm not going to write I squared. I squared is negative 1. I have negative 2 square roots of 15. Okay, I squared is negative 1. Square root of 4 is 2. I took the square root of 4, but there's still a square root of 15 left underneath. Same thing here. Please don't write this as the square root of 10. You have to take I out first. In this case, okay, I understand that I do get, because the i's cancel, I end up getting the square root of 10. That's fantastic. Okay, but you still want to make sure that you're taking I out first in case you end up with an I squared. With division, the i's canceled. Okay? So, in this case, I have I square root of 48 over square root of 24. I can go ahead and divide 48 by 24. This is I square roots of 48 over 24, which is what, 2? So I get 2I. You notice there's an I there. There was nothing to cancel it with. Okay? When we add and subtract, we simply add the real parts and add the imaginary parts. I think of it as combining like terms. I literally think of the I as a big fat X. So I'm like, this is 3 minus 4I plus negative 2 plus 6I. I drop the parentheses because I was adding. There's nothing to distribute. So I add these together, and I add these together. 3 plus negative 2 is 1. Negative 4I plus 6I is positive 2I. Here, I have to be careful because I'm subtracting. So I'm going to distribute the negative through. And then I combine like terms. That gives me negative 10 plus 10I. Okay, that's how you add and subtract. Not too bad. FOIL, we're going to do just like we did before. Okay, 2 times 3 is 6. 2 times 4i is 8i. Negative 3, we get 9i. And then minus 12i squared. The difference is I squared is negative 1. So I still combine these just like I did before. 8i minus 9i is negative 1i. But here I have negative 12 times negative 1. That's positive 12. I can add that to the 6 and get 18 minus I. I'm going to do the rest and show the answer. And I'm going to do that in the next video.